Video, we want to look at a more challenging problem of how to find the distance between a point and a line. So we've already determined how to find the distance between 2 points, and we've done a lot of work with lines, but now we want to find the distance between a point and a line. So let's first of all consider a very, very simple case. Let's pretend we had this line right here, which would be x equals -3. And let's say that we had the point 3, 1, which would be right there. This is fairly trivial. We all know that the distance between the line and the point is 3. But it's actually a little more complicated than that. In reality, we have to first of all say, how do we know how far a point is from a line? Because there really are an infinite number of ways I could go from the point to the line. I could take a path that looks like that. I could take another path that looks like that, and there are an infinite number of possibilities. We all know from common sense that I want to take that path, and what's special about that path is that it's perpendicular. You could think of this as a real-life example of a person standing a certain distance from a wall, and if they were going to race to the wall, they would want to go along a line that's perpendicular to the wall in order to get there in the shortest distance. So we know that the shortest distance between a point and a line is along a line, or along a line segment that is perpendicular to the given line. Now let's apply that in a more complicated case, because in this case it's obvious that we have 3 units to get to the y-axis, and we have to go 3 more units to get from the y-axis to 3, 1. So we would have to travel 6 units to get from the line to the point, or vice versa. So let's look at how to do this if the line were not a vertical line. Obviously, or hopefully it's obvious. If the line instead had been a horizontal line, we could easily construct a perpendicular and know how far we are from the horizontal line. So let me erase what we have so far, and let's start over with a more interesting problem, where we consider what would happen if we were given the line y equals 2x plus 1 and the point 3, 1. So we want to find the distance between the line and the point. So let's start by sketching the line. So put my y-intercept at 1, over 1, up 2. We have a slope of 2, so we can sketch in what the line would look like. And then we start coming down over here by dropping 2 and going over 1. And we have a series of points. We can sketch a nice line through those points. So that's my line y equals 2x plus 1. My point 3, 1 is right here. So now to find the distance to the line, to go get the shortest distance, we would need to go along a path that is perpendicular to the line. So the easiest thing to do algebraically is to find the equation of the entire line that contains the segment from the point to the line. So we want to get the equation of the red line. Now we know how to do that. So all of the steps of this problem are things that we've already done. Okay. So the key is that the red line is perpendicular to the green line. So we want to start by finding the equation of the perpendicular line. Okay, to do that, we know that y, it must have a slope of -1/2, so we have -1/2 x, but we don't know where its y-intercept is yet, so I have to leave b as an unknown. So the y-intercept is up here somewhere, and we don't know exactly where that will be. It looks like it's somewhere in the vicinity of 3, but we don't know exactly what its value is. We got the -1/2 because it's a negative reciprocal of the slope of 2 for the original line. So now how do we find the value of b? Well, we know that our point, that the perpendicular line runs through the point 3, 1. So we can substitute 1 in for y and 3 in for x. And we can say that 1 is equal to -1/2 times 3 plus b. We can solve for the b value. So let's go ahead and do that. Since we're going to be in halves, I'll let 1 be 2 halves, and then we'll have negative 3 halves plus b. Add 3 halves to both sides, and we get that b needs to be equal to 5 halves. Okay, so it looks like if I had drawn this a little bit better, the y-intercept probably should have been right about there. I was sort of guessing at where the perpendicular line would intersect the original line, but my line that I'm looking at must really be about there, and you can see it looks like it's perpendicular to the green line. So my original sketch was off by a little bit, but not by too much. Okay, so now we have the equation for the perpendicular line that y is equal to negative 1/2 x plus 5 halves. In order to find the distance to the line, what we're really going to need to do is start at our original point 3,1 and find the point of intersection of the two lines, and then we can find the distance between those 2 points as we have in the past. Okay, those will form a nice little triangle. It has a delta y value and a delta x value. So now we're in part 2 of the problem. Part 1 of the problem was finding the equation of the line perpendicular to the original line that ran through the point that was given. Now we need to find the point of intersection. We know the point 3,1. We have to find the coordinates of the point of intersection. So let me do that right over here and say we now know that 2x plus 1, which is the equation of the first line, the right-hand side, should equal negative 1/2 x plus 5 halves. The easiest way to solve this is to multiply both sides by 2. So when I do that, I would end up with 4x plus 2 on the left is equal to negative x plus 5. So that clears out the denominators by multiplying both sides by 2. Now add x to both sides, subtract 2 from both sides, and we end up with 5x is equal to 3. Okay, so the point of intersection must be that x is equal to 3/5. Okay, so that is the x value for the point of intersection. We still need to find the y value. So in order to find the y value, we have to go over and substitute into one of the original equations. So y should be twice 3/5 plus 1. So that would end up being 6/5 plus 5/5, or 11/5 in total. So that makes sense. It's a little more than 2. So the x-intercept is less than 1. Or I'm sorry, the point has values of 3/5 comma 11/5. 3/5 being a little less than 1 and 11/5 being a little more than 2. So that looks like a reasonable answer for our point of intersection. So the final part of the problem, so that was sort of phase 2 of the problem. The final part of the problem is going to be now to solve for the distance between the 2 points that we just found. To do that, as in the past, we want to know how much the x value changes between the 2 points and how much the y value changes. And then once we have those, since those form a nice right triangle, we can invoke the Pythagorean theorem to find the actual distance. So when we put our numbers in, we can first of all find delta x by taking the x value 3 and subtracting the x value of 3/5, and we can find delta y by taking the y value of the second point and subtracting the y value of the first point. So when we take 3 minus 3/5, that'll be 15/5 minus 3/5, so that gives us 12/5 as our change in x. When we look at our change in y, 1 would be 5/5 minus 11/5 gives us a change of 6/5. So now, to end the problem, we have to figure out, using the Pythagorean theorem, what the square root of delta x squared plus delta y squared is. And this won't be a nice answer. We're used to math problems often giving us nice answers, but the answer to this will be clearly a radical. So we're going to have 12 over 5 quantity squared plus 6 over 5. Oh, I'm sorry, that should be negative 6/5 because the y value dropped. But that won't matter because we're about to, when we look at this, we erase that and get the negative sign in there. We're going to square this quantity anyway. So when we square a negative value, it will be positive anyway. So what matters is that the size of the vertical side is 6/5 in length. So if we work through this, we get the square root of 144 plus 36 all over 25. Both terms have the same denominator. So we can add 144 and 36. And when we look at that, 150, 180, we have the square root of 180 over 25. Okay, so when you look at that ratio, if it had been 175 over 25, it would go in evenly. We would have 7. So the square root of 7 is less than the square root of 180 over 25, but it's clearly less than the square root of 8. So the distance should be more than 2, and it should be clearly less than 3, but getting close to 3. So the distance between the 2 points is the diagonal. So it's somewhere around, probably more than 2.5. And if you want to find out that exact value, you can't get the exact value because it's a radical number, an irrational number, I should say. And so to get the value of that, you would need to grab your calculator and get an approximation of it. And in doing that, let me see here real quickly. Let me put the numbers in. 180 divided by 25 is 7.2. And when you take the square root of that, you get an answer that to 2 decimal places would be 2.68. That's not exactly what the answer is. The answer is exactly what we have expressed already, although we could reduce it by dividing both numerator and denominator by 5.